Yeah, hello everybody. It's really nice to see full house after some time at the Institute. Yeah, I'm really glad about that. Okay, as a host, the Jožef Stefan Institute, I want to greet our visitors today. In particular, Professor Atish Dabholkar, who is visiting us from the International Center for Theoretical Physics in Trieste. You are our neighbors, so finally we have you here. I'm really glad you could make it. So today we are looking forward to your lecture, but today we really have a special honor. We have Her Excellency Namrata Kumar, the Indian ambassador here. Hello. Yeah, we're really glad that you will attend this lecture. So I don't want to be too long. I want to pass to Professor Martin Kleinschek, who is in charge of our Institute seminars, to tell us a little bit about our guest. So I'm sure that everybody will enjoy the next hour and something new that we potentially will learn through this hour. Okay, thank you very much.
Thank you, the director. Okay, I'm also really glad that you came in such great numbers here. This is the first time after COVID that we filled up the whole lecture hall. Welcome to the 5th colloquium of this academic year. This colloquium today is joined with the physics colloquium at the faculty, and this is also part of the reason why you came in such great numbers. As usually, I will first introduce our today's speaker, which I'm also honored to host here. So Professor Atish Dabholkar is a theoretical physicist from India and currently the director of the Abdus Salam International Center for Theoretical Physics, as already said. In short, ICTP, the people know it, this institution after this abbreviation, in Trieste, Italy. He is well known for his research on string theory and quantum black holes, including investigations that built on ICTP founder Abdus Salam's Nobel-winning work on electroweak interaction. Professor Dabholkar is a graduate of the Indian Institute of Technology at Kanpur, one of India's premier educational institutes. He earned a PhD in theoretical physics from Princeton University, followed by postdoctoral and research positions at Rutgers University, Harvard University, and California Institute of Technology. Until 2010, he was a professor of theoretical physics at the Tata Institute for Fundamental Research in Mumbai, and has been a visiting professor at Stanford University and a visiting scientist at CERN. He joined ICTP in 2014 on a secondment from Sorbonne Université and the National Center for Scientific Research, this is NRS, in France, where he has been a research director since 2007. At ICTP, he was a head of the high-energy cosmology and astroparticle physics section. He has received many honors, including the Shanti Swarup Bhaktnagar Award in 2006, the most prestigious National Science Prize awarded by the Indian Prime Minister, for his outstanding contributions for establishing how quantum theory modifies the entropy of black holes, and his pioneering studies of supersymmetric solitons in string theory. He is an elected member of the Indian Academy of Sciences, and in 2007 he received the Chair of Excellence Award from the National Research Agency, ANR, in France. So, Atish, please, I am passing you the word now.
Okay, dobar dan. Najlepša hvala za tako prijazen uvod. V veselje mi je biti tukaj z vami. Prihajam iz Indije, delam v Trstu, živim pa v Sloveniji, na Primorskem, saj je moja žena Slovenka. Čudovita država je, lepa narava, prijazni ljudje. Tudi v svetu fizike poznam veliko kolegov slovenskega rodi. Prav je za moj govor relevantno delo Jožefa Stefana, ki je odkril, zelo poznam Stefan Boltzmannov zakon, ki je izjemnega pomena za teoretično fiziko. Ko bom govoril o črni luknji, za vas bo bilo manj boleče, če govorim v angleščini. Okay, so I would like to tell you briefly, and I realize that this is a broad audience with many, about some very exciting, this is really a frontier of research now, has been a frontier of research for some very, very exciting work on quantum black holes, very surprising connections between the work of Hawking, which has to do with black holes, of course, but also Ramanujan, a great mathematician. So I'm going to very quickly, some of you are, many of you are, at least more than 60% of our physicists, so maybe this is a bit of a repetition, but I'm going to go slow so that everybody is on board, at least for the first few slides. So one of the great discoveries of the 20th century physics is the relativity of time, which follows from the fact that the speed of light is the same whether you measure it standing on a platform or whether you're in a moving train. And this is very counterintuitive, because if you have a ball, cricket ball or football in a train, which is at zero, it's not moving, if you're standing on the platform, it will look to you like it's moving at the speed of the train. But that doesn't happen for the speed of light. And that's very strange, and that is only possible because the time measured by the person on the train is different from the time measured by the person standing on the platform, and that's called the relativity of time. Now, it's a very strange thing, but basically it says that the moving clock runs slightly slower, and therefore the speed of light is the absolute speed limit. You cannot exceed it. And what is relevant for my talk today is that this has two very dramatic implications. One is the existence of gravitational waves, and the other is the existence of black holes. And both of them sort of follow from this basic idea. So this is a very nice simulation by Brian Greene on this world science. You can see if you have a clock which tells you running the time about just by once the light comes down, that's 1 unit of time, then you can see that the clock on the moving train runs slowly, basically because of the Pythagoras theorem that light has to travel longer distance since it is moving. It is going on the diagonal. So that's the essential reason. If the speed of light is constant in all frames, then just by Pythagoras theorem it follows that the time must be relative. And this is a calculation that even a 12-year-old high school student can do. So now what does that imply? It implies gravity waves. If the sun disappears, this is a question for non-physicists, that if the sun disappears just now, when will we come to know about it? You might think, some of you might say immediately, if you know your high school Newton's law of gravitation, because Newton's law of gravitation says that the force of gravity between the sun and the earth is proportional to the mass of the sun and mass of the earth divided by the distance square between the two. There is no time in that equation. And therefore, if the mass of the sun goes to zero, the force will go to zero immediately without any delay. But I just now told you that the speed of light is the ultimate speed limit. So this cannot be right. And this is what bothered Einstein for 10 years. And he succeeded in creating the general theory of relativity, which predicts that also gravity must travel at the speed of light, and that is called a gravitational wave. And this was a prediction of Einstein's equations for 100 years, and it was only very dramatically observed very recently, which earned 3 physicists Nobel Prize recently, in 2016, I think. So this is gravity waves. What about black holes? Again, I want to motivate black holes from this basic principle that the speed of light is the ultimate speed limit. So you know very well that if I throw a rock, it will fall there. If I throw it faster, it will go further down. If I really throw it very fast, it will start going around the Earth. And if I take a rocket and I shoot it up at the escape velocity, which is quite high speed, then it will escape the gravitational attraction of the Earth. But now if you make the Earth heavier and heavier, imagine the Earth is really a big star, then what will happen is that the escape velocity will start increasing. And at some point, if the Earth is really very dense or very small or very dense, let's say, then the escape velocity will be the speed of light. And then nothing really can escape the Earth. No rocket will be powerful enough to escape the force of gravity. And such an object is called a black hole. So therefore, so I have told you that just from this simple fact that the speed of light is the ultimate speed limit, two very dramatic consequences follow. One is the existence of gravitational waves, and the other is the existence of black holes. And so this is the artist's impression of a black hole. And this is a very, there is a more mathematical way of stating what a black hole is, which is called, the black hole is surrounded by something called an event horizon. It's like let's say, it's a one-way surface. So imagine that this is the event horizon. Then it is a stationary surface, but which at the same time is moving at the speed of light. It's something that you cannot imagine in normal space, normal geometry. But in the kind of geometry, Ramanujan geometry that is used in general theory of relativity, this is possible. So imagine this is a wall that looks like it's there, so it's stationary, but it's at the same time it's moving at the speed of light. Then once I cross this, I cannot come back because I cannot travel faster than the speed of light. So I will always be inside the wall, on the other side of the wall. So that's the basic idea of a black hole. A more intuitive way of saying it is that basically the force of gravity, as I've said before, force of gravity is so strong that it pulls even the light downwards, and light cannot escape it. But there is a more mathematical way of describing the same. And essentially, once you fall inside, you cannot come out, no matter how powerful are your rockets. And you will be met with a very unfortunate future, that there will be a singularity in your future, and in which you'll be pulled into kind of spaghetti, so it's not very pleasant. And this was predicted by Chandrasekhar, that once a star slightly bigger than our sun runs out of the nuclear fuel, then nothing can stop the inward pull of gravity, and the star will collapse. And actually, it's very interesting, the history of, many times the history of science is very interesting, especially black holes make a very interesting study. But almost for 50 years, nobody believed in black holes. In fact, Einstein himself wrote a wrong paper trying to argue that this singularity cannot occur in nature. And many people really opposed Chandrasekhar so violently that Chandrasekhar had to leave United Kingdom and go to the US. I think people like Arthur Eddington were really appalled by this idea. And this very bizarre conclusion is actually true. But the actual observational evidence took 100 years. And here is the observational evidence. It's really a fantastically amazing experiment. This is the LIGO experiment, where there is a 4-kilometer long laser beam is going back and forth. And if a gravitational wave passes through, it shakes that arrangement a little bit, laser beam a little bit. And from how much it is shaken, you can detect that a gravitational wave has passed. Of course, it gets shaken up even when a truck passes through, and you have to subtract all that background. So it's a remarkably delicate and very amazing experiment, just from the experimental point of view. And the theory is also very amazing, because what you're observing is 1.2 billion years ago, two black holes from far away merged into a single black hole. And basically, because mass is equal to, E is equal to mc square, if the mass of the final black hole was much smaller than the sum of the two masses, then there was an enormous amount of energy, which actually was more than the energy of all the stars at a given time, was released, but all in the form of the gravity wave, which you cannot see. And that reached us 1.2 billion years ago, which it has started after 1.2 billion years ago. And it's just when, we, sort of the descendants of monkeys, we had figured out how to make a laser, and we had this experiment, and we detected it. So if you think about it, it's rather extraordinary that some little planet far away from these black holes, and these monkeys managed to detect. So this is the general theory of relativity. As I told you, Einstein was trying to make sense of this idea that the speed of light is the ultimate speed limit, but Newton's law of gravitation then doesn't fit with it. And in order to resolve that contradiction, he was led to the general theory of relativity, so that the relativity of time is more general. I think the general means that not only when the train is moving at a constant speed, but if the train is accelerating. So Einstein figured out what happens if the train is accelerating, how to formulate this. And that is called the general theory of relativity. So the relativity really refers to the relativity of time. And so it generalizes Newton's law and predicts gravity waves and black holes. But this is only one part of the story. The other part of the story, as all of you know, here is the quantum theory. So general theory of relativity, which is the Einstein's great discovery, great achievement, I think it has been hailed as one of the greatest achievements of the human mind. And it's really truly remarkable. It's a beautiful, simple equation you can write down, and you can predict all kinds of things from the expansion of the universe and black holes and whatnot. But the other side of the story, so that works at a very large distances, the universe or the galaxy or black holes. The other side is also equally amazing, and in fact has been even more influential, as you know, in the 20th century, which is the quantum theory, which describes nature at a very, very short distances. And it has been enormously successful in describing atoms, molecules, and the physics of the atomic nucleus. It underlines much of the modern technology, from semiconductors to this laser that I'm pointing here. It all depends on quantum theory. Without it, you cannot describe it. And it predicts an antiparticle for every particle. For example, every electron has an anti-electron, proton has an antiproton. Now, so we have this situation in the 20th century physics that you have these two big pillars. One is general theory of relativity, and the other is the quantum theory. They both work amazingly well in their respective domains. But if you try to bring them together, if you try to marry them, it's a very disastrous marriage. And it basically, there is a very fundamental contradiction between quantum theory and general theory. And I won't be able to describe it more fully. But roughly speaking, if you include the quantum effects into account, it looks like that the attraction between the sun and the earth will become infinite, rather than you expect that the quantum theory should correct Newton's law of gravitation only slightly. Instead of that, it gives you an infinite answer. And this really cannot be acceptable in a consistent theory of nature. And so this has been a quest for almost 70 years now. People really wanted to figure out how to marry quantum mechanics with general theory of relativity. And that is where string theory comes into picture. So we want to have a consistent quantum theory of gravity where these two cornerstones of modern physics work coherently together as one single theory. It's kind of unifying these two ideas. And unfortunately, this is a very subtle contradiction at some level, and therefore very difficult to observe experimentally. So you need more subtle theoretical tools to really figure out how we can test, even if you come up with some theory. And this is where the physics of the black holes continues to be very, very powerful tool. It's almost like it provides you a kind of a theoretical microscope by which you can study this. And this is where Hawking comes in, one part of the hero of the story. So Hawking discovered that because of, so I told you, a black hole is black. It's called black because it's really nothing is black. Even light doesn't come out of it, so it's really black. And it's a hole because it's really a hole in space-time. So it's really a black hole. But Hawking showed that actually black hole is not really black. He showed that black hole is actually like a hot piece of coal or hot piece of iron. It's slowly emitting radiation, even though I just now told you nothing can escape its force of gravity. So how does this happen? And so it's very much like a piece of metal. It's really, black holes are hot, in some it's not a cold object somewhere. It has some temperature. So how can it be that something which I told you gravitationally cannot allow you to be let anything escape? How does it allow you to have any radiation coming out of it? And the idea is that you need to use quantum theory in a fundamental way, and this is called Hawking radiation. So as I told you, one of the important consequences of quantum theory is that for every particle there is an antiparticle. And in fact, in this room, constantly there is a particle and antiparticle gets created and gets annihilated. We don't notice it because it happens, I don't know, in 10 to the minus 15 seconds, so we don't notice it. But if it happens near the horizon of a black hole, for example, like this, here, then what can happen is that the antiparticle can fall inside and the particle can escape without violating the law of gravity, because this was happening outside of the black hole. So you don't have to violate the speed limit. So that's good, because you don't want to violate the speed limit. But there is an uncertainty, there is an uncertainty principle. So there is a bit of a fuzz about where the particle is created. If it's created just a little bit outside, one partner can fall inside, the other partner will escape. And this is the origin of Hawking radiation. This is a very famous discovery of Hawking. It's called the Hawking evaporation process of a black hole. And he showed that a black hole is not really black. And Hawking actually has when I was a professor at Tata Institute, we had invited him to India, and he has a connection with also India. He visited Bombay, and it was very interesting to have him here as well. He was one of the speakers at the conference that we had organized there. So now the question becomes, how do we understand something? How can a black hole have temperature? I told you it's like a hole. It's like a hole here. How can something which is pure space, there is nothing inside, how can it have temperature? Because, as you know, all of you, if you have studied your statistical physics, that and Jožef Stefan had a very important role in the creation of the statistical physics, that with the work of Boltzmann and originated in the observations of Stefan, that's why there is a Stefan-Boltzmann law. In atomic theory, we understand the temperature of anything which is hot in terms of the motion of the particles that make up that thing. So, for example, this room is hot, the temperature goes hot, because the air molecules are bouncing around and they hit your body, and that's how you actually have the sensation of it being hot. If you put a heater and things become hotter, then what is happening is that the air molecules are moving more faster and faster, and so the temperature goes up. So the higher the temperature, there is a motion of some atomic constituents of matter. And that's what is causing let's say, a piece of matter to be hot. Like this room is hot because the molecules in this room are moving faster. Now you can ask the question, what makes the black hole? Why is a black hole hot? What is moving? What are the atomic constituents of a black hole? And for that, Hawking had no answer. And this is where string theory comes into picture, and that ultimately leads to Ramanujan in a very interesting way. So I'm going to remind you very quickly, so I'm doing good on time. So I have another 20 minutes or so. So 20 minutes? Yeah, okay. So I'm going to explain to you, for the physicists this would be a repetition, but for those of you who are non-physicists, and some of them are here, there is a very important concept called entropy, which originated starting with Stefan's work, but a very brilliant theoretical physicist, Boltzmann, who really introduced this concept actually it was introduced before him by engineers like Carnot, who were trying to design efficient steam engines. And they came across this notion of an entropy. And the notion is very simple, but I will explain to you why it's a very fundamental concept in physics. So entropy is a very subtle and profound concept in physics, and it explains why heat flows from a hot body to a cold body, but never the other way around. Right? If you put two bodies together, and one is at a higher temperature than the other, heat always flows in one way and never the other way? Or why is it that, it's much easier for me to break an egg and splatter it, but you never see suddenly the egg that is on the floor assembles and becomes a nice egg? Why is it? Why does it happen like that? And that can be explained by this notion called entropy and the second law of thermodynamics. And it is defined very simply. The change in entropy is basically change in the heat. So suppose you put a heater in this room. You can measure what is your electricity bill, and you can calculate using joules how much heat is being given. And the change in the heat is something that you can measure. And it is happening at the room temperature. And if you do this process slowly, that defines this notion of entropy, that entropy is basically change in amount of heat that is added to the room divided by the temperature of this room. So it's a very simple concept to define. But the reason it is fundamental, okay, and then the second law of thermodynamics says that this quantity defined in this manner always increases. So that's the second law of thermodynamics. And this explains why why heat flows in only in one way, and as I will explain to you. And what Boltzmann and other physicists realized, like Maxwell, that entropy is really an intrinsic property of a given system, like let's say the gas in this room or this any piece of metal. The entropy of that object is a property of that object, and it's not. It's really like energy of the object. It's some intrinsic property of the. And now let me explain to you why heat flows only in one way. If you accept the second law of thermodynamics, suppose I have a hot body next to the cold body, right? The heat given by the hot body to the cold body is delta Q, but it's a temperature 1 upon T2, and heat received by the body is delta Q divided by T1. Sorry, it's the other way around. I have done T1 is greater than T2. So the heat obtained by the cold body is delta Q positive, 1 upon T2, and heat given out is negative, it's given out, divided by T1. And now if delta S, the total change in entropy, has to be positive, T1 has to be greater than T2. So second law of thermodynamics explains this very well-known, well-observed fact that heat flows only from hot to cold. Now what does it have to do with black holes, and what does it have to do with matter and atoms? This is where Boltzmann comes in. Boltzmann made this very, very amazing and important observation that entropy, which you can measure by, putting a heater and measuring the temperature, it's really a macroscopic, It's at the level of human beings. You can measure it. He suggested that the entropy of a given system, let's say at a given energy, is logarithm of the number of ways the atomic constituents can arrange themselves with the same energy. So for example, in this room, if we fix this room and no energy can go out, if it's completely sealed, then the energy of this room is fixed. So we know the total energy of this room. But the various atoms can move in many different directions, and there are many, many, many ways in which this room can exist. And that number of ways, you take the logarithm of that, and Boltzmann tells you that logarithm is equal to the entropy of this room, the gas in this room. And using this, he was able to deduce that you don't see atoms. You see, we believe that the world is made of atoms because in school you studied it. But if I ask you, prove it to me that there are molecules in this room, how will you do it? Boltzmann didn't have a microscope, but Boltzmann deduced that the world is made up of atoms by having a model in terms of atoms and calculating the entropy, and he showed that it actually matches with the observed entropy. So this was one of the Stefan-Boltzmann law you can derive in this manner, this famous temperature to the power 4. In this manner, he was able to explain that why the world is made up of atoms. And this is where our connection to Boltzmann comes in, that we are trying to understand what makes up the black hole, but we don't have a microscope to look into the black hole. So what we are going to do is think about the entropy of the black hole and try to explain it. And that explains also the disorder, but I will skip that. So one of the properties that what Hawking showed was that the black hole has temperature. But if anything has temperature, then it must have entropy. Why? Because it has mass, the black hole has mass, And the first law of thermodynamics says that total energy is equal to the total heat given. But heat is temperature times the entropy. So if something has non-zero energy and non-zero temperature, it must also have non-zero entropy. And from that, he derived a very beautiful formula that the entropy, a black hole has entropy, even though it looks like a black hole, and it is proportional to the area of this horizon. So there is a big sphere, imagine it's a big sphere of radius of the event horizon. So 4 pi r square is the area, divided by 4. That, according to Hawking, is the entropy of this black hole. So suddenly, we are making some amazing connection between quantum mechanics, general theory of relativity, and thermodynamics. You know, you might ask, where does thermodynamics come into the picture? Because you have temperature, you must have entropy. And now, because of Hawking, we can make a connection to try to figure out where does this entropy come from? What is the little pieces that are vibrating to make up the black hole? Just like we could figure out the atomic structure of matter, can we figure out the atomic structure of space and time using this black hole entropy? So that's the fundamental reason why the entropy of black hole is such an important quantity, because it allows you to sort of look inside the quantum structure of space-time, even though you don't have a real microscope to do it. In the same way that Boltzmann was able to look at the atomic structure of matter, even though there was no microscope at his time. In fact, Boltzmann committed suicide near Trieste because for a large part of his life, part of the reason was perhaps he was unhappy with his own life, but he was also unhappy because the atomic hypothesis was not accepted by many physicists, many chemists at least, for a long time. So it was only in the 20th century that this became. So we sort of take it for granted nowadays, but atomic hypothesis was not accepted. So what are the atoms that make up the black hole? And that's where string theory comes in. So I will just give you a very quick introduction of string theory. So string theory basically postulates that instead of electrons and protons being particles that are moving around, they are little pieces of string. Okay? And it turns out that it has to live in 10 dimensions or 26 dimensions. It sounds all very science fiction-y. But the main idea is that just like a violin string, the string can have different notes. It can be like a do, re, mi, fa. And each note of the string corresponds to a separate particle. So if you want to have a photon, it's like a do. If you want to have an electron, it's like a mi, and so on. So the strings theory was it looks like a very, almost a childish idea that, okay, instead of point particles, you're turning them into string. It turns out it's extremely rich. And in fact, general theory of relativity just comes out of string theory without even having put it in. That was actually one of the big surprises, that people didn't want to look at string theory as a theory of gravity. But suddenly they discovered that one of the modes of the string, one of the notes of the string, is the graviton, and therefore it is a theory of gravity. And there is a photon, so it's a theory of Maxwell. So basically every beautiful theory of nature that we had understood seems to be contained in one of the modes of the string, if you really understand string theory properly. So different notes, so basically an electron is one kind of a note, and a proton is another kind of note. That's a kind of a cartoonish idea of string theory. And it has some extra dimensions. As I told you, it lives in 10 dimensions. So we live in these 3 spatial dimensions and time, but you have these additional dimensions according to string theory, which can be curled up into little balls. So at every point in our space, there is a little ball, which is a 6-dimensional sphere, let's say. You wouldn't really see it in our normal, but it could be there, and we don't know. And string theory requires, for reasons of consistency, that it must have these additional dimensions. But even though we cannot see these little balls, we can see them through black holes, and this is how the connection with black hole comes. So imagine that you are a little insect moving on a wire. So you take a long wire. The long wire actually is, the surface of the wire is 2-dimensional. You know, you can move this way and go around the wire. But if the wire is really thin compared to your body size, then you would imagine that the wire is only 1-dimensional. And that's the basic idea of the compactification, that these dimensions can be very small. Now you can imagine a string that is wrapping this many, many times. It would look to you like a little particle in the remaining long dimensions. So that's the basic idea in this picture of a black hole in string theory, that it's like a more sophisticated string, but there is essentially a string that is wrapping many, many times. And it looks like a point particle in your big space, which is 3 plus 1 dimension, with 3 spatial dimensions and 1. But inside, it's really like a little string that is oscillating. Okay, so you get now, but if you have a string, it can oscillate. And if you suppose have a string that is oscillating in, say, if you're living in 26 dimensions, so you take the string is stretched in one direction, time. So there are 24 transverse directions in which the string can oscillate. So imagine that a string that is oscillating in some internal space which you cannot see. Then there are many ways the string can oscillate. It can oscillate this way, it can oscillate that way, it can oscillate with long wavelengths, it can oscillate with short wavelengths. And that, it turns out, in many black holes that are found in string theory, is the origin of entropy. Because as I told you, entropy is the logarithm of the number of ways you can make that object. So if the black hole is made up of strings, then depending on which way the string is oscillating, there are many ways that the same black hole with the same mass could arise by many different ways in which the string is oscillating. And that's where you come to a very beautiful connection with Ramanujan. So the string can oscillate in many different ways. Sorry. I'm going to show you some movie just quickly. Sorry, I'm going backwards. So the problem becomes like this. This problem I'm not going to explain to you how, but how many ways the string can oscillate reduces to finding how to partition an integer into many different ways. So just to give you an example, so I told you the string can oscillate in 24 different directions, okay? This problem can be mapped to a very simple mathematical problem, and the problem I can state very easily. Suppose I give you an integer n, okay? How many ways can you write that integer as a sum of other integers? But those integers are of 24 different colors. So just to give you an example, how can you partition number 3, let's say, using red and brown, red and green. So you can write 3 is equal to 1 plus 1 plus 1, 1 plus 1 plus 1 red, or 2 plus 1, or 2 plus 1 red, or 3, or the other way around. So there are 10 different ways you can obtain. So the 10 different ways, if you take the logarithm of that, that is somehow has to be related to the Boltzmann's entropy formula. So that's what we want to do. This is the counting problem. So what I have done is now, I have reduced this beautiful physics of black holes, general relativity, speed of light, to a very simple counting problem. How many ways can you partition this integer, some large integer, in terms of 24 integers, in terms of other integers of 24 different colors? And this problem has a long history, and it goes back. There was a famous, so this is Ramanujan. Ramanujan was a 24-year-old mathematician who was discovered by this. There was a great number theorist at Cambridge, Hardy. And Hardy received this letter from somebody in Madras saying that, dear sir, I have proved something very interesting, maybe it's of interest to you. And he had sent this letter to many mathematicians and nobody paid attention. But Hardy immediately realized that this is really a work of a genius. He said that this is somebody of the same class as Euler or Jacobi. This is a mathematician of very high caliber. And he invited Ramanujan to come to Cambridge. And when he came to Cambridge, his colleagues were very skeptical. And in particular, Major McMahon, a combinatorics, he worked on combinatorics. He was, in fact, asking exactly the same problem that I've given you. How to partition an integer. Use not 24 different colors, he was saying only one color. How to partition an integer.
Enter at your own risk. Ah, I've been waiting for you. Square root of 58,639. Now.
242.
242 what?
0.1549090.
Yes, child's play. Try me.
Go on.
Same number squared.
3,438,532,321. Ah! thrashed you. Combinatorics, that's what I do. Glorified dice throwing. Bloody nerve of you both. You fail on primes, and you think you can just turn round and crack partitions. Can't be done, I'm telling you. Especially not by you.
It can. And I will.
No, I will. By hand. By slow and painful addition, and then you can be absolutely certain that whatever formula you two can dream up will be quite wrong. Then you can crawl back under whatever rock you came from in India, and we can put to bed this charade of yours, Hardy. Now, how high do I have to go?
P of 200 should do. I really can do it.
And McMahon says, no, there's no way you can solve this problem. It's too difficult. And they test each other. I mean, McMahon says, tell me the square root of a very large number. And Ramanujan tells him. And then Ramanujan says, okay, so they are kind of sparring with each other. They're fighting with each other mathematically. And then he says, okay, what do I have to do to convince you? So he said, okay, why don't you tell me the partition of the number 200? Now, you can try to do it, okay? Imagine 200 is a small number. But think of how many ways you can partition it. That number actually grows very rapidly. You can write it as 1 plus 1 plus 1 plus 1 200 times, or 1 plus 2. If you start writing it, it's actually millions or billions. The number grows exponentially. And that's why McMahon thought that nobody can really solve this problem. So Ramanujan had discovered a beautiful formula, and it goes like that. If you want to partition an integer with 24 colors, it goes as exponential of 4 pi square root of n for a large integer. And in fact, I will come to it. Now this should remind you, if p of n was the quantity whose logarithm Boltzmann wanted to take. So what this tells you is that if you take the logarithm of this, 4 pi square root of n would be the entropy of the black hole, okay, of the corresponding black hole. And in fact, people have checked, including my work is in fact in this area, that you find a really beautiful agreement between Hawking's formula of area divided by 4 and this 4 pi square root of n of Ramanujan. So basically next time this movie is about that he goes back to see Major McMahon, and Major McMahon says, okay, tell me what you have gotten. And he says, okay, 3,235,000,000, etc., and it's on the dot exactly the same number that McMahon has calculated by laborious methods.
Well, here we are, P of 200, the moment of truth. You know, I was stationed in Madras once. Yeah. Well, you first. What has your formula given you?
3,972,998,000,000.
My God. You're close. Within 2%. Well, I'll be damned.
Major McMahon, may I introduce you to Mr. Ramanujan?
So basically, this to connect it to black holes, I'm almost done. So using Ramanujan's formula and more sophisticated versions of Ramanujan formula, I have given the most simple example. We have been able to actually essentially check that in string theory, this idea of the black hole is made up of this winding strings a little bit, going this way, that way, oscillating that way, this way, which you can calculate the number of ways in which the black hole is composed by using Ramanujan's formula. How many ways can you partition an integer? Roughly, that's the problem that you have to solve to understand how Ramanujan's formula can be applied to black hole physics. And then you take the logarithm of that quantity, and that gives you the entropy of the black hole. And it's really on the dot. It's actually very impressive when you do the calculation. I mean, it's really, really long and very difficult calculations. And you do it from both sides, where completely different calculations. So on one side, you're trying to find a black hole solution. It's some differential geometry, Riemannian geometry. You find some solution. You calculate this area divided by 4. The other side is you're doing some counting problem, which is purely combinatorics. And magically the two things in the end are exactly equal. So that gives you some confidence that maybe string theory is on the right track. I mean, we still are not sure whether that's the theory which unifies gravity and so how did Ramanujan do this? Okay, I just want to tell you now. I can switch to a bit for the physicist. What he did was that he defined a partition function, which is what all physicists do when you're doing a partition function. But he said that define a function q times z of q, which is 1 plus q square plus q cubed to the power 24. Sorry, here there is a typo. It should be 1 plus q square plus q to the power 4, q to the 6 to the power 24. And you multiply all these. And now if you want to compute this p of n, which McMahon was telling him, then you just look at the coefficient, you just expand this, just multiply. You can do this on a computer, it's not difficult. You just multiply each of these brackets and look at the coefficient of q to the power 200. And that's the number that will give you p of 200. That is the Ramanujan's formula. But what allows him to do this is, so you can use this famous geometric series, 1 plus x squared is 1 upon 1 minus x. So this partition function looks like this, 1 upon q, 1 upon 1 minus q, 1 upon 1 minus q square. And this function is to the power 24 actually. I have forgotten here to put the 24. And this function is an example of what is known as a modular form. And modular form is an object, mathematical object of great symmetry. You imagine, like if I draw a figure, square. Square is symmetric if you rotate it at 90 degrees. But a sphere is even more symmetric. A circle is even more symmetric because you can rotate it any which way, it comes back to itself. A function, so you do something to that object and it comes back to itself. That defines the symmetry of that object. And these modular forms that Ramanujan discovered have this beautiful symmetry that it's a function of some variable t. It's basically related to 1 upon the t. So if you calculate the function z of 1 upon t, you will get back essentially the same function. See, this is if you take a sine function, for example. The sine function is periodic. That's correct. But imagine if you take sine of x, it's not the same as sine of 1 upon x. So a generic function is very far from being a modular object. If you take x square is not the same as 1 upon x square. So modular functions are this very special class of very symmetric functions. And using this symmetry, and this comes up in the statistical mechanics also. This is related to what is known as the Cardy formula in statistical mechanics. It basically relates the partition function, physical partition function at temperature T to temperature 1 upon T. This is the basis of the Hardy-Ramanujan's work actually has applications elsewhere. And using this formula, Hardy and Ramanujan were able to find this very beautiful expression. In general, log of Pn is 4 pi square root of n to leading order. But it actually has an infinite expansion and all the terms they were able to calculate. And quite amazingly, now in string theory, there are examples where you can calculate from the black hole side, not only the area upon 4, but all the corrections, the quantum corrections to the black hole entropy. And again, they magically agree beautifully. So I think this gives you some confidence that maybe string theory is not so far off the real. So this is the road ahead. There are really an exciting discoveries and exciting frontier of research. It's not easy, but very definitive progress is happening. And for any one of you, the younger researchers, I think it's a frontier that you should at least read about, and maybe you want to work on it one day. So, Nail Epshawala, I will just, before I end, I would just like to show this slide to you. This is where I'm the director, the International Center for Theoretical Physics. It's here. This is our building. It's right across the Grad Miramare. There's a beautiful park here. In fact, in the summertime, we almost always go for a swim. In the afternoon, it's really next to the sea. And many of you, including Martin, has told me, we have 6,000 scientists visit ICTP. It's a major just to show you, just to tell you a bit about ICTP, and I invite all of you to visit it when you have the chance. It was founded by the Nobel laureate Abdus Salam, and it's governed by the Italy International Atomic Energy Agency and UNESCO. We welcome 6,000 scientists. I mean, we have about 400 people on campus any given time. Permanent staff and students and postdocs. And we welcome, in addition, 6,000 scientists from all over the world. So over the years, some 200,000 scientists from 188 nations have come to ICTP. 30% of them are women. And each year we have 60 very high-level conferences, workshops, and activities. And the idea of Salam, which is very close to my own heart, I mean, coming from India, he was from Pakistan, is to create an international hub for science, which can help overcome the barriers of geography and gender or ethnicity and economics to make scientific resources globally available, and also use science as a vehicle for creating international understanding. And in fact, even during the Iron Curtain days, the Soviet scientists and American scientists or Chinese scientists could meet in a neutral place, and that place was ICTP. So you can see here, this is a beautiful picture of really, you see a rainbow of student body. These are our master students. So this is a special place, and I hope that in future, it's right close to Slovenia, and many of the Slovenian physicists have been here. So I will stop here.
Yeah, thank you very much for this really interesting, amusing talk. Also very broadly accessible, I would say. So first of all, regarding Boltzmann, I heard that he committed suicide for trivial reasons.
Trivial reasons.
You know, the woman and so on.
No, I don't. I don't know.
I was told so.
No, it's possible. I think, yeah, I think it's not fair to blame it on atomic hypothesis. But it could have been the contributor. I mean, he did struggle throughout his life to get acceptance for his ideas. This is also true. But yeah, you're right that those may not be the reasons why he committed suicide.
Okay. Well, these are the words that my high school professor used, and I remember them. Okay, but now I think that we might have a lot of questions. We have a lot of students here, and as we know, students are the best in asking questions, interesting questions.
Yeah, please feel free to ask questions.
So yeah, just raise your hand, and I will bring the microphone.
No question is dumb. Okay, so you should.
Yeah.
Don't feel that you're not asking.
So you have the first question. No.
This was just meant privately.
Okay. Later. Okay. Okay, great.
So I will refer, thank you first for your nice talk. I will refer to the second line of your conclusions, so experimental evidence.
Yes.
I wonder whether there is any, even indirect, experimental evidence for Hawking's radiation.
So, unfortunately not, because the temperature of a black hole is inversely proportional to the mass of the black hole. So the larger the black hole, the lower the temperature. So you cannot really directly measure it. However, people have tried to make some analog systems in which there is a black hole. But so it's not a real black hole, but it's I mean, you can sort of mimic, let's say, if you could mimic, instead of having a speed of light as the limit, some other speed on some condensed matter system as the limit, then people have tried to construct such condensed matter systems where there is a limit to how fast you can travel and there is a pair creation. And then they have tried to mimic the Hawking effect there. But I would say also that this general idea of a creation of particles in an accelerating or in a gravitational field, indirect evidence for that is the cosmological primordial perturbations. So those are, for that there is a direct experimental evidence that cosmological primordial perturbations are believed to have been created by, again, a quantum field in a curved background in the early cosmology in an expanding universe. And it's a very beautiful, actually, it's a very striking experimental and very important experimental observation confirmed by the Planck observer recently, a few years ago. And that you see these Gaussian perturbations. So what happens is that this during inflation, there are small quantum fluctuations which get amplified because of the expansion of the universe. And you now try to correlate that with what you see in this Big Bang hot, the microwave background radiation. And the spectrum of perturbations of a microwave background radiation matches very well with the idea of quantum fluctuation generated by a quantum field in a gravitational field. So the basic idea of Hawking radiation, I think, is fundamentally correct, but to finding evidence for it. So I think this is actually an example where one should not be, I mean, there is sometimes, and I'm saying this, I mean, of course, experiment remains the final arbiter in a theory of nature, whether we accept. But oftentimes, there is a long gap between experiment and oftentimes physicists proceed by way of consistency and the strength of the theoretical arguments, including, let's say, the discovery of the Higgs particle. It took 50 years to discover the Higgs, but people were convinced about it for 50 years. And the gravitational waves took 100 years. So it is a delicate, it's a good question, and but I think for Hawking radiation, one can only hope for indirect verification and not direct experimental verification.
Thank you.
So I'm sorry if this is a dumb question, but
no, as I said, no question is a dumb question.
A vibrating string has infinitely many modes of vibration. Like, does that imply that there are infinitely many particles? Like,
yes, a very good question. It's actually a very good question. So, in fact, this is one of the expectations from string theory, that not only should you see particles that we observe, like an electron and a graviton and so on, and a photon, but there should be a whole infinite tower of particles. However, there is the more shorter the frequency of oscillation, the bigger the mass of the particle. So therefore, you see a very massive particle, since they are beyond the reach of the current LHC experiment. So if the next massive particle and the next massive particle are much heavier than the observable particles, then you will not see them in observation. But they are nevertheless necessary for the consistency of the theory. In particular, one of the big achievements of string theory was that it could resolve this paradox between quantum theory and general theory of relativity. I didn't go into that, but it gives a consistent theory of quantum gravity. And in order to achieve that, it's really important to have this infinite tower of states. So, but there is no direct observation.
Hi. First of all, I want to place on record a great appreciation, deep appreciation for your presentation. This has taken me back to my physics classes, which I did only till the first year of my undergraduate course, and reminded me that I wish I had focused a little bit more on thermodynamics. My focus was more on the nuclear physics, which interested me more. But that also tells me that, you know, you have to study every part of physics equally with equal stress, so that you can bring them together to learn better concepts. That was one thing. Secondly, you so beautifully explained such complex concepts to everybody, so it was understandable to the layman also like us. And thirdly, that while coming to your lecture, my colleague said that, you know, today I'm really feeling good that this is another part of India which is not Slumdog Millionaire, but different. And I said, yes, India is really not bothered at this point of time to fight against the cliched images that it has been facing with for many years now. But we are more invested in works like yours, which will speak about what India is doing, has been doing, right from Ramanujan till you and beyond. And more importantly, bring the global community together, yes, irrespective of the nation's priorities. Now I come to question, and which is linked to my previous question asker, is about your string theory. So it's again a very, very from the layman point of view, that, you know, why are you visualizing this as a string? Could it not be some other shape?
A membrane, okay. This is actually
some other shape, like, you know, an amoeba, a three-dimensional shape moving in different directions.
I think it's a very good question.
Hitting, you know, the particles within that are hitting in all directions with
No, so-
those 24 color combinations, and then when they are at the periphery of the black hole, they have many possibilities of going inside and going out. So
No. So I think it's a good question. So it's when I try to describe it like a violin string, but what we are talking about is a relativistic string, the string that moves at the speed of light. So it turns out that trying to formulate a consistent theory of the motion of such a string, it looks like a very trivial extension, almost like a childish extension, as I said. From a point particle, you think of it as a string. Okay, then why not a membrane, and why not? But it turns out that for the string, you can actually do the quantum theory completely consistently in a very unique way. There is a very strong internal structure to string theory, which you do not observe in other, if you try to quantize other membranes, other shapes. However, these other shapes, the other membranes, do play a role in string theory, and they are called D-branes and membranes, P-branes. They do play a role, but not at such a fundamental level as a string.
at the ease of calculation.
No, but also in terms of, yeah, so I think it is now, I would say that the membranes do play a role, but their understanding their quantum theory is far from easy.
I would just like to have a comment. You said that Hawking actually defined the entropy of black holes, but I don't think this is true. I think it was Bekenstein.
Yes, I mentioned Bekenstein and Hawking.
Okay, thank you.
Yeah.
Thank
So,
you. Because
but what is true is that, see, Bekenstein, so it's actually a very interesting story. Bekenstein was a graduate student in Princeton, where I was also a student. And he asked a very simple-minded question. He said that, okay, you told me that the black hole, nothing can come out of a black hole. So now what happens if I throw a bucket of hot water or a cup of tea into a black hole? Then the entropy of the cup of tea will go inside the black hole. So therefore, I can violate the second law of thermodynamics. So Bekenstein reasoned, just from, again, consistency, that if I believe in the second law of thermodynamics, and I believe in the black hole properties of a black hole, then it must be the case that the only way the second law of thermodynamics can be saved is if the black hole also has entropy. So that when you throw a cup of tea into the black hole, the entropy of the outside world goes down, so it seems to violate the second law of thermodynamics, but the entropy of the black hole must go up. And just by this kind of a very heuristic thought experiment, Bekenstein correctly concluded that the black hole must have entropy. But then that raised a problem. If the black hole has a mass and it has entropy, then it must have a temperature. But on the other hand, if it is temperature, then it must radiate. But a black hole is black, so nothing can actually come out of it. So Hawking really showed that it has temperature. So he took the heuristic idea of Bekenstein, and he really was able to calculate that the entropy is not only proportional to area, but it is proportional to area divided by 4 with G, with all the h bars and C, all the constants there.
sorry, Bekenstein got it right, the numbers.
No.
By 2 phi.
Yeah, no, but Bekenstein did not have a calculation of the entropy of the black hole.
No,
the temperature of the black hole. And therefore, he was not able to calculate the precise coefficient.
Not the precise coefficient, but he got it pretty much right.
Pretty much right, but not the precise coefficient. But what is missing is not just getting a 2 pi versus 4. What was missing was what is the physical mechanism by which the black hole has temperature. That Bekenstein had not explained, which Hawking explained.
Yes,
so which is why it is correctly called the Bekenstein-Hawking entropy formula. So you're right that Bekenstein absolutely deserves equal credit for the Bekenstein-Hawking entropy formula. But the temperature of black hole is the Hawking temperature. And the discovery of Hawking really...
Entropy is Hawking, but not temperature.
Temperature... okay.
Okay, maybe I suggest that we shift this little discussion, little duel to the time after the colloquium. Okay, so do we have any other questions? Okay, yeah.
This is actually a sub-question, as the superstring theory predicts infinitely many particles, and in the standard model, there are three generations, like electron and that mu particle, muon, and the tau particle. So should there be actually infinitely many generations, or does it go in other directions?
Okay. No, I think it's a very good question, I should say, because the three generations of particles that we observe are for mostly low mass particles. And as I said to the previous question, most of the string theory excitations are very heavy mass. But you can ask now, what about these three generations? Does string theory have a natural explanation for that? And that was one of the early, it's a very attractive idea. I mean, one doesn't know if it is true or not true because it's difficult to experimentally find any evidence for it. But it's a very pretty idea. What people were able to do was to relate the number of generations of low energy particles to properties of this internal manifold. So you have a 10-dimensional theory which is compactified on some 6-dimensional things, so you only see large 3+1 dimensions. And what they showed was that some topological properties of this internal manifold, like the Euler character, is related to the number of generations. And therefore, the number of generation is finite. It's not infinite, and it is related to the Euler character of this internal manifold. But I think it's a very good question, and it was one of the important, interesting discoveries in the early days of string theory.
Okay, thank you. Other questions? So I would really like to encourage the students to ask questions. These are the most interesting ones, the most challenging ones, I guess. So, do we have any brave student here?
Yeah, you have to stick your neck out.
Okay, maybe I will ask some question. One question. So I'm wondering this factor of 1/4 in the expression for the entropy. Can it be understood in some simple way, like in some phase space partition or something like this?
So, no, I think in Hawking's derivation of that 1/4 really depends on calculating the temperature of the black hole, which is 1/8 pi m, the mass of the black hole. And that calculation, okay, there is a geometric way of understanding it from some Euclidean continuation of the black hole solution, from the periodicity of the Euclidean continuation of the black hole solution. But I wouldn't say that it's a simple, it's not some simple thing like a phase space factor. It is a geometric, it's related to a geometric property of the black hole rather than.
And doesn't have to do with this number of dimensions?
And it doesn't have to do, yeah, the amazing thing about that area upon 4 is that it's true for all kinds of black holes, rotating black holes in higher dimension. It's a very universal formula.
Okay, thank you.
Can you maybe say something, a brief overview on the information paradox regarding black holes?
Okay.
Maybe current state or
current
ideas.
Status, yeah. Okay, so the question that he's asking is the following. So I think in a black hole is full of very exciting paradoxes. And as I've told you, just thinking hard about what looks like a trivial paradox sometimes can lead to some very deep insight, as was the example with Bekenstein. That he said, how is the second law of thermodynamics to be saved? And he said, okay, then the black hole must have entropy, right? But then Hawking said, okay, then how is the first law of thermodynamics to be saved? Because then black hole must have temperature. Now, that raises a question that if the black hole radiation is really thermal, then suppose I throw in Encyclopedia Britannica Volume 1 into the black hole, then the black hole entropy will go up, and then it will radiate out purely thermal spectrum. It looks like a hot star emitting radiation. Now, if I throw in an Encyclopedia Britannica Volume 2, it will give you exactly identical looking thermal spectrum. So that raises the question, what happened to the information that was contained in the Encyclopedia Britannica Volume 1 and Encyclopedia Britannica Volume 2? The two things, even though have the same mass, have very different information. Now, this is actually a very fundamental property in physics. I mean, I'm simplifying it a bit, but there is something called the unitarity in string theory, which is very fundamental. That information is conserved in the unitary time evolution, which is a fundamental axiom of string theory, so of quantum mechanics. And therefore, it raises this puzzle, which Hawking immediately pointed out. he says that, okay, it looks like information is lost, and therefore there is a fundamental contradiction between black holes and quantum mechanics. So even though he arrived at the temperature of the black hole using quantum mechanics, it was leading you to a contradictory conclusion. And this turned out to be a very deep question to which we still have not found the answer. But there has been some very exciting development through holography, which says that the amount of information contained inside a black hole. See, normally if you take a room, the amount of information contained in this room, you would think is proportional to the volume of this room. Because you can have a little bit, quantum bit at every point, and therefore the number of bits you can put inside is equal to the volume of the room. But Hawking-Bekenstein formula suggests that it must be proportional to the area of this room. And that's why it was called a hologram. That is, as though all the information in this room is contained in sort of on the walls of this room and not on the volume of this room. This sounds almost bizarre, but there is now very, very strong evidence that actually this kind of holographic description of nature must be true when you are dealing with quantum theories of gravity. But that still has not completely resolved the information paradox, I would say. I think the current status is that there is every indication that there is no paradox, that quantum mechanics is right, and information comes out in a very complicated way. See, I mean, this question could be asked also for the star. You see, the sun, you throw in Encyclopedia Britannica inside the sun, what happens? What happens actually is that there the information actually does come out. Because the sun is constantly, so there is a difference between the sun and the black hole because of the causal structure of the black hole, because of the event horizon. And therefore the information paradox, there is no information paradox for the sun, but there is apparent information paradox for the black hole. But I think most physicists, including myself, believe, but I think I would not say the issue is settled. We are far from a really complete resolution of the information paradox.
Okay, thank you. We have the last question here.
Hello.
Yes.
So this would be the third question going about these infinite particles. So let's say that we have some massive particles, and they could probably also form like particle and antiparticle, like you're saying at the event horizon. Shouldn't like this increase the Hawking radiation a lot, and could we detect some, let's say, decaying light from these particles? Okay. So this would be a question.
Yeah. So the answer to that question is that, see, the temperature of a black hole is inversely proportional to the mass of the black hole, according to Hawking's calculation. Now, if you take a black hole of some reasonable size, that temperature is very low. It's like in micro Kelvin. So at that temperature, it's very difficult to excite a particle whose mass is much, much bigger than the typical temperature of that. So typical, like in this room, right? You see, only when you raise the temperature of this room will you start seeing, particles of higher and higher. You don't see very high energy photons, right, in this room. You see only low energy photons because the temperature, the frequency, the wavelength of the photon is determined by the temperature in this room. If you raise the temperature, then you will start to see gamma rays. So to go to higher energy, the temperature of the black hole has to be very high. Now there were some ideas like in extra dimensions. The people were hoping this was an idea, but it turns out not to be the case. That when you are doing this Large Hadron Collider experiments, if there are extra dimensions, then the temperature of that black hole could be brought down, could be raised up to the energies comparable available at the LHC experiments. If that happens, then some of these very massive particles, which correspond to some states in the Kaluza-Klein states, they were called in the extra dimensions, could be seen. Because you will form a very small black hole by a collision of two particles. Therefore, the temperature will be very high. And then you could try to see some massive evidence for string theory or some extra dimensions. But it turns out that, there was no such observation. But it was a very interesting scenario which was discussed and explored by many physicists. But that doesn't happen in nature.
Okay, thank you. I'm sorry that I have to interrupt this interesting discussion because we have some duties awaiting us. So thank you everybody for asking questions, and thank you, Atish, for having us this giving us this really interesting talk.
Thank you. Thank you.